I guess I'll start with a little preamble. So we've done books 1 and 2. Book 1 concluded with the proof of the Pythagorean theorem, which was, what was the number? 48? No, 47.
Yeah, something like that, yeah.
Book 2 was a lot of stuff about squares, and concluded with the proof of the law of cosines, sort of a generalization of the Pythagorean theorem. But basically there wasn't a lot of circles in book 2. It was triangles and squares. I think there was one circle in the final proposition, if I remember correctly. Book 3 is moving back to talk about circles. So I'm unsure how much of the definitions to write down. Maybe I'll just read through them and sort of presume you're looking at the definitions as well. So maybe we can read through them and make any remarks we need to make. So book 3. So definitions. Equal circles are those the diameters of which are equal or the radii of which are equal. So this is remember, equality for Euclid doesn't mean coinciding figures, right? It's not like a set of points in the plane. He often says equal squares to just mean that they're equal in area. And so equality has several different senses, actually, and you need to be aware of that. Often we're flagging that, sometimes we're not. A straight line is said to touch a circle, which, meeting the circle and being produced, does not cut the circle. Yeah, so I guess is that clear? So he's describing this situation as being something that doesn't meet the circle twice. Circles are said to touch one another, which, meeting one another, do not cut one another. Yeah, so again, one point of intersection. I don't know to what degree these are really well-founded on the earlier axioms, and I don't really want to get into it right now, but maybe we could at some point. In a circle, straight lines are said to be equally distant from the center when the perpendiculars drawn to them from the center are equal. I think that's clear. That straight line is said to be at a greater distance on which the greater perpendicular falls. Yeah, we know how to compare lines because we have a theorem lemma that says that given any line and another line, you can cut off a part of the former line, which is of length equal to the latter. So that's how we can tell that two lines are, that a line is longer than another one, whether there's something left over or not. And we don't need some notion of length as a number in order to do that. A segment of a circle is the figure contained by a straight line and a circumference of the circle. Yeah. An angle of a segment is that contained by a straight line and a circumference of the circle. An angle in a segment is the angle which, when a point is taken on the circumference of the segment, okay, maybe I should draw this. So this is 8. An angle in a segment is the angle which, when a point is taken on the circumference of the segment, so this is a segment. The segment is the whole figure, I guess. Is that right? It's a figure contained by a straight line and a circumference. So yeah, I guess it means this part. An angle in a segment is the angle which, when a point is taken on the circumference of the segment and straight lines are joined from it to the extremities of the straight line, which is the base of the segment, is contained by the straight lines so joined. Yeah, okay. So I take a point on the circumference and straight lines to the extremities of the straight line. So this. So it's this angle here. Okay, so it's not the angle of the segment, it's an angle in a segment. I hope that's clear. When the straight lines containing the angle cut off a circumference, the angle is said to stand upon that circumference. When the straight lines containing the angle cut off a circumference, the angle is said to okay. So I think it means that. So the blue angle stands upon this circumference. Generally speaking, these definitions become clear in the context, so we don't need to dwell on them too much. A sector of a circle is the figure which, when an angle is constructed at the center of the circle, is contained by the straight lines containing the angle and the circumference cut off by them. Yeah, that's clear. Similar segments of circles are those which admit equal angles or in which the angles are equal to one another. No idea what that means. Let's see what it means in the context of a proof. Unless it's clear to you. Okay, so proposition 3.1. To find the center of a given circle seems like a useful thing. Maybe just this time, since we're resuming, I'll go back through the propositions that are going to get used and remind you what they say. So we're going to use proposition 1.8, which I've gotten rusty on these early ones. Proposition 8 says, if two triangles have two sides equal to two sides respectively and also have the base equal to the base, they will also have the angles equal. So it's the standard criterion for equality of two triangles. I definition 10 is just the definition of I definition 10. Oh, that's sector of a circle. I think that's all we're going to use, perhaps. Okay, so let's proceed. As usual, there's some kind of bad habit with naming things, making use of points that are going to be constructed but haven't been constructed yet, which bugs me a bit. But so I'm just going to say, let a circle be given. So it's required to find the center. As Kenneth knows, we all love the sentences that involve drawing random things. So let a straight line AB be drawn through it at random. Yes, it's actually a little. What do we actually take this to mean? Obviously, we don't. We sort of have to name a point in connection with this circle, otherwise we can't even get started, right? So partly finding the center is partly about being able to name any point in a way that doesn't involve making a choice, right? If we just have a circle sitting on the board, then it's hard to see that we can actually name any point. I don't see any way around that. I think in context, we'll have other points that we care about, and we could always use one of those to start off this construction somehow. So if we have like some line over here, well, we have some points, and then we can always extend this line and see if it cuts it. If not, draw a line perpendicular and like eventually somehow get a line that intersects our circle or something. So I feel like in the context of later proofs, I could probably, through shenanigans like that, avoid this terrible random thing, but I guess we'll just live with it. Okay, so let's draw a line at random, AB, bisected at D. The book I'm reading from doesn't cite which proposition that is, but we know we can do that. From D let DC be drawn at right angles to AB. Again, we know we can do that. And we let it intersect the circle at, I apologize for the background noise, at C and E. It doesn't matter which side these are on. And let CE be bisected at F. Okay. We claim F is the center of the circle. So let's prove the claim. For a contradiction, suppose G is the center. Of course, we don't know that centers are unique, right? I think that's actually like really what we're proving. So what's the center of a circle? Well, by definition, a circle is a set of points that are equidistant from some point. I guess we don't know that the points could all be equidistant from more than one point, right? So what we're now supposing is, well, so to say the center is to say that it is a center plus it's unique, right? Okay, so I think we're going to prove both. So maybe I should say not the center, but a center. So that is to say, suppose that there is another point G which has the property that all points on the circle are equidistant from G. And we're going to join GA, GD, and GB. All right. Since AD is equal to DB, by construction, and DG is common, the two sides AD, DG are equal to BD, DG respectively. Let's see. AD, DG should be equal to BD, DG. Yeah, well, that's what we just said. And the base GA is equal to the base GB. By the hypothesis that it was a center. So that means by proposition 8, ADG equals the angle equals GDB. Okay, but when a straight line set up on a straight line makes the adjacent angles equal, each is a right angle. Okay, so both of these must in fact be right angles. But FDB is also right. So FDB equals GDB. Right, so I've got FDB and GDB both being right angles, but one is contained in the other. Right? GDB is contained in FDB. So that's a contradiction unless G actually lies on the line CE. Which is impossible. Unless G on CE. Why can't that be the case? Well, if G was on CE, this is not in the proof, but let's just think about it for a bit. So let's suppose G were up there, then you could use Pythagoras to see that in fact GA, what would that say? Actually, why is that impossible? Yeah, okay. So if G were on the line CE and it were not at F, that would mean it's not bisecting CE. But you see, this and this would have to be equal because they're both radii. But that can't be the case unless G bisects CE, right? Well, more to the point, these two lengths would have to be equal, right? GC and GE would have to be equal, so G would have to bisect CE and therefore be equal to F. So we're relying then on the uniqueness of the bisection of a line, which I guess we probably didn't prove, but is, yeah, that's easy enough to see. Okay, I'm done. How are we doing for time? Ken, do you have time for the second one?
Oh, I think we've got about 10 minutes left. I think I should be able to get through 3-2.
Yep.
Once again, we're talking about circles, and we're going to use 3-1. We're going to use the fact that we can find the center, and we'll see if we actually have to, do random things. I think we might. So let's see. Okay, so the proposition states that a straight line joining any 2 points on the circumference of a circle lies inside the circle, falls inside the circle. Okay, so
I feel like we already used that somehow in the proof of proposition 1, but anyway.
Yeah, I mean, yeah, it feels that way, but let's see. So we have to draw a circle. Hopefully I can draw a reasonably good one. There we go. So we're going to use the previous proposition to find the center of the circle, which we'll call D. Let's get back to, right. There we go, D. Okay, we're going to call the points on the circle, right? Let's suppose we're given these points, A and B. Okay, and we're gonna join these. So let me just put down here. This is by proposition 3.1, right? Finding this D, center of the circle. So I'm going to join. What happened to the colors? I was trying to find yellow. I guess there you go. I'm going to join D to A and to B, and we're going to assume that A and B, right, for contradiction, that A, B does not lie inside the circle. So we're going to draw this line here, which you have to pretend to be straight. And of course, we can't draw a straight line because that's impossible. So we're gonna just do that, and then we're gonna say that there's a point E here, which is outside the circle, and we're gonna join up this this line, or D and E, and have it intersect the circumference at F. Okay, so that's the construction that we're going to use to prove that, in fact, this construction that we just wrote down leads to a contradiction. Okay, so proof. I'm going to fit it here. Won't fit on this page, but we'll go to the next page if we need. So suppose AB does, let me see, write this better, does not fall inside the circle. Okay, then there's a point E, which we already kind of picked, E on AB. On AB, which is outside the circle. Okay, so then I'm just kind of writing down what I constructed over there. So we're going to join D and E and call F the intersection of DE with the circumference, with the circle. Circumference of the circle. Okay, so then we're gonna do some angle stuff and derive a contradiction. So we're gonna go to the next board. I don't think I have to move for this. I'll just switch over. Right. So we're gonna refer back to propositions in book 1, and there's no way you're gonna remember the numbers for this, but I'll refer to the numbers and I'll tell you what the proposition says. So by proposition 1.5. So I think that proposition is the one that tells you that a triangle with two sides being equal, basically, as you know, a triangle with two sides being equal have the two angles opposite these sides, they're also equal, right? So essentially, this is the isosceles triangle proposition, right? Since maybe I'll write better. So dA and dB are equal, right? Because they're radii of a circle. The angles DAE and DADBE are also equal. And of course, these are the angles that are opposite the equal sides of this isosceles triangle, so they have to be equal. And now we're going to use proposition 1.16. So this one says that the external angle of a triangle is larger than the opposite internal angle. And I guess we go back to the picture over there. Well, this is a really wonky triangle, right? Basically, it says that this is the external angle. This is the external angle. And this over here is the opposite internal angle. You're going to have to pretend that that red line is straight and that DAB is actually, well, DAEB, right, is actually a triangle angle. And the claim or the conclusion of 1.16 is that DEB, which is this external angle, is larger than the opposite internal angle, which is DAE. So let's go back and write this down. So by proposition 1.16, the angle, so this is the external angle, DEB. DEB is greater than DAE, which is the opposite internal angle. Okay. And this means that DEB is actually greater than DBE, because DBE we showed earlier is the same as DAE, right? So this is from before the same, right? So I'm just putting the inequality that we had earlier with the equality, right? So now the final kind of piece of argument is that, so now we've shown that, let's go back to the picture. Let's go back to the picture here. I'm gonna use different color here. Like this angle is now bigger than this angle. So I put the two stripes here to indicate that two pink stripes indicate that that's bigger than DBE, right?
Oh,
but
I see. Mm-hmm.
That also means that this DB, right? So this is also larger than that one. And you can probably see here that this is gonna be impossible because radius, right? So that's how we derive the contradiction. So it's actually similar to the previous proof of the previous proposition, right? You put one thing inside another, right? We did angles previously, now we're doing lines, right? So the proposition
really nice.
that yeah, it's pretty nice. So the proposition that tells us this is actually 1.19. I'll remind you what this says. So by proposition 1.19, right? This is the one that says that the larger angles are subtended by larger sides in triangles, right? So basically, the larger angles are subtended by larger sides in triangle, right? So that's quick, brief recap of what it says, right? So, you know, by 1.19, the conclusion is that DB, right, which is the radius actually, is greater than DE, right? And this is impossible, right? So the last line of the argument is that DF is actually part of DE, right? Is part of DE because that's inside, right? We've said that DE is actually outside the circle, right? So DF must be part of DE, right? And that DF is a radius that's equal to DB, right? So this is impossible. Cool, and that's it.
Nice.
Awesome.
Yeah, I like that. I kind of missed the circles. There's something nice about the circles in Euclid.
Yeah.
Too much. The squares last book were a bit boring.
Yeah.
I was looking ahead a bit. I don't actually understand like what the culmination of book 3 is. It seems mostly like
a bunch of circle facts.
Yeah, I mean, Proposition 36 is pretty interesting. I feel like if I thought about it, I could say like what that actually says in modern terms, but I couldn't see it just yet. There's lots of interesting facts. I think it'll be fun, but I don't think it's leading to like some big theorem at the end, at least as far as I can tell.
I see. Well, there's a good number of propositions here, so it'll keep us busy for a few weeks.
Yep.
Cool.
All right. Well, we're done for today. Thanks, everybody. That was fun.
Cool.
Glad to be back with Euclid.
Yeah.
Thanks.